Welcome to the third video of designing a power supply. And the good news is we're going to end up with a power supply that actually may be useful. So we can work on after we finish this, we can actually use this power supply to support some of the other projects we're going to be dealing with. Okay, so design a regulated power supply. It says that we had an unregulated power supply, and we found that a change in the input voltage resulted in a proportional change in the output, which means that it's not particularly stable. We can't rely on the output voltage. And also we had this ripple problem. Remember, the ripple, we can minimize the ripple by increasing the capacitor, but as we pull more and more current out of that power supply, we would increase the ripples. So there's kind of a fight that goes on here that's a really hard one to solve. We solve this by using a diode regulator, okay, and the diode regulator basically made our output voltage modestly independent from the input voltage. So let's go through and see what the problem with the diode regulator. Diode regulator, as you can recall, is basically this set of this resistor and a stack of diodes, or Zener. Better yet, a set of Zeners. We can do a set of Zeners for this. The way this works is that the forward voltage drop of the regular diodes, the reverse voltage drop of the Zener, basically has a fixed point here. So this potential tends to be fairly constant, independent of the raw voltage, so independent of the input voltage and a bunch of other things. So then we could get a pretty constant V out over here. So this is a far superior to the other one, to the unregulated. Now, here's the problem with it, is that every bit of current we pull out here, every electron flowing through here, is going to flow through this way. So we have this problem with this resistor. If the resistor is too big, we have a problem that we are limited to the amount of current we can pull through here with before the resistor's potential drop becomes so large that the diodes no longer can conduct. And if it's too small, then we end up dissipating a tremendous amount of power through here, especially when we have no load on the power supply. So this is only good for very, very small currents. Okay, here's what we're going to do. We took this identical supply, we copied it down here, and we added this thing to it. Okay, this thing is a transistor. And here's what the transistor does. It's a 3-terminal device. And so we can see one terminal, which is called the collector, another that's called the base, and another that's called the emitter that's sitting right here. So collector, base, emitter. And what happens is that the current flowing from the base to the emitter controls how much current is flowing from the collector to the emitter. And a matter of fact, it does it through a proportionality constant, which is a fairly large number. So we can use a fairly small base current to control a very large collector current, and this gives us some amplification. The trick here is that since most of the current is coming through the collector, we no longer have such severe limitations on the size of this diode resistor. So that's how we're going to gain some benefit by adding a transistor. Okay, I didn't do a very complete job of explaining the transistor, so let's look at the transistor in and of itself. As I said, it's a 3-terminal device, collector, base, emitter. Okay, in order for this to work, this has to be properly biased, okay, which means the outside circuitry must be added to this 3-terminal device so that the collector potential is above the base potential and is above the emitter potential, okay? If you fail to keep this relationship honest, then the transistor will no longer work. Okay, so let's take a look at the easiest part. And the easiest part, I think, is the base, this flow of current and potential, or the potential between the base and the emitter. The base and the emitter, as indicated by this kind of little arrow here, behaves like a forward bias diode. Okay, using standard silicon technology, the base to emitter drop is about 0.7 of a volt. And it's pretty constant, just like the diodes. Okay, and then obviously we know from our junction rules that the emitter current is, the way we have things defined, is the sum of the collector current and the base current. So we have this fact too. So given those two facts, let's add one more fact, then we can actually see how a transistor is going to help us. Okay, we already have that the emitter current, is the collector plus the base current. Then here's where the transistor becomes very useful. The collector current, when the transistor is properly operating, is equal to some constant, we call it beta, okay, times the base current. Okay, so since beta is a number between about 10 and a few hundred, or a few tenths to a few hundred, is that we can actually end up with a situation where a relatively small base current can cause a very large collector current to flow. Okay, so if you will, the transistor is acting like an amplifier. It amplifies the base current into the collector current, and since the collector current is the primary component of the emitter current, then it also goes through and increases the emitter current. So we can use the base current as the control for how much current is flowing through the collector and the emitter. So if we put this thing together, we look like this. The first thing that we notice is that the potential between the base and the emitter is about 0.7 of a volt. Okay, and that's because it's a diode. Okay, we find that for every milliamp of current going into the base, we generate about beta milliamps going through the collector. And since we have this junction rule thing going on, that charge is conserved in a transistor, thank goodness, is we find that the current that's flowing out the emitter is equal to the base beta, which was the collector current, plus 1, which is the base current, times the base. Okay, so we have the transistor operating like that. Now let's go back into the circuit and see how all this thing works. So let's return to our transistor regulator. So here's its redrawn, okay, and so the base potential, let's say, is 2.1 volts. Why? Because this stack is 3 times 0.7, so that's about 2.1 volts. Okay, since the base in the emitter is a forward bias diode, we know then that this point is approximately 1.4 volts. Okay, so then we can see what would be the current required through this resistor to have this potential 1.4, because this part is, we generally will set this to ground potential. And so we find that use Ohm's law is that ILRL is equal to 1.4 volts. Okay, and that says that the current that's flowing into the load or out of the emitter, and this is really important to understand, that notice that these two currents are the same current. The load current and the emitter current are the same current. So the amount of current flowing there is just 4 volts, which would be the output voltage, okay, divided by the load resistor. Now, then we can turn this around and say, well, what is the base that's required here? What's the base current? Well, we notice that the base current is equal to the emitter current divided by the gain of the transistor plus 1, that's beta plus 1. We just substitute what we found in here for the emitter, which is this value, and so this point right here is the emitter current, and then we find the base voltage is this. Okay, so how does that help us? Because we've taken the base voltage and we divided it, base current, and we divided it by beta plus 1, which is the number like 50 or 100. And so it means we really have a low base current coming out of here. Another example here, and we find why it's useful, is let's go through and let's see if we can, because we have small base current here, that means we can have larger values here, okay, than what we had before. So let's look at a 2.1 volt, 1 amp power supply with the raw voltage of 12 volts. And so we have 12 volts up here. And we have a beta of 50 in this transistor. Okay, so when we have a fully, oh, by the way, did I make a mistake here? Let's see, there's 1, 2, 3, 4 diodes. So why do we add the fourth diode? Because we had a diode drop here. So if we wanted an output of 2.1 volts, we had to add a fourth diode to counteract that drop here. Because we don't want this point now to be 2.1 volts, we want this point to be about 2.8 volts. That's a terrible 8, but I think you know what I meant. Yeah, that's even a better 8. Okay, so here's what we do. So when we fully load the base current, let's go through and see what this thing is. When we have the smallest load resistor possible for our design, we end up with a base current, or with a load current of 1 amp, which means we have an emitter current of 1 amp. Okay, so what is the base current? The base current is 1 amp divided by 50 plus 1, and that's about 20 milliamps. Okay, so if we need to have a little bit of current through the diodes, this ID, and so this is the potential across this resistor. This is the current through the resistor, the maximum current through the resistor, and now what do we find? That resistor is 420 ohms. Now, why is that important? Because previously, when we did not have that transistor, that resistor, RD, if I remember correctly, was a little bit less than 10 ohms. And 10 ohms, it required a lot of power dissipated across this resistor. So we've actually improved this quite a bit by going through and using the transistor to source most of the current out through the collector to the load, rather than relying on all the current to go through the resistor. Okay, now, you know, if a beta of 50 works, wouldn't a beta of like 1,000 work even better? And the answer is yes. Okay, because if we look at the gain of this transistor, the lower this base current is, the bigger this diode can be, or this resistor can be, right? Because we're pulling less and less current. As a matter of fact, ideally, you'd want this just to this diode, or this resistor here, to just support enough current to support this diode. By the way, this diode's a Zener now, and so we've plugged it in backwards, and then this will generate something. Maybe this is like 6 volts or 10 volts or whatever the reverse breakdown voltage on the Zener is. So what we can do here is, there's limitations on how much gain we can get out of a single transistor. But let's put 2 of these transistors in cascade. So let's see what happens here. Suppose both of these transistors have a beta of let's say, you know, let's have a beta, the same beta. So if we squirt a little bit of current through here, we get a potential drop. Okay, but the main thing we get here is the amount of current now flowing into the base of the second transistor is beta times the amount of current that was flowing through the base of the first transistor. And then similarly, how much current is flowing out of the emitter of the second transistor? It would be beta squared times the amount of current that's flowing in through here. So we can actually go through, and by using 2 transistors here, to go through and actually increase the equivalent gain, current gain, of those transistors. This is named after an electrical engineer, Darlington. And this is the Darlington transistor. It's actually 2 transistors in one package. You don't actually have to put these 2 transistors together. Okay, we can get it. We can buy it as one convenient package. It's kind of a supercomputer, or super transistor, I'm sorry. And so it's basically the product of the betas, or the square of the betas. And what we do is we can reduce this current, this base current, by another factor of beta by doing something like this. Now, so we have basically a regular transistor, we have a Darlington pair, and then let's see what we do. So the physical transistor we're going to use is a 2N 2222, okay? This is a PNP, which is the one we've been describing, and it's in a TO92 package. The TO92 package is this package right here. It's a little plastic package with 3 leads coming out of it. 1 lead for the base, 1 lead for the collector, 1 lead for the emitter. These are also other packages that you can get, not necessarily for this transistor, but these are packages. The first transistor I saw when I was in high school, believe it or not, was from General Electric, and I got about 1,000 of these transistors, these cans, okay? I haven't seen one in a long time, okay? Most of the transistors are shipped like this. You actually have some chip transistors that are surface mount, very, very small, okay? You can also go through and get a package like this, which would be higher power, and then higher power still for packages. So there's many different packages. The same thing. They always have 3 leads coming out of them: base, emitter, collector. Okay. In our case, what happens is we look kind of like a truncated cylinder here, a cylinder with side sliced off. You can see it from the bottom view. The emitter is the lead on this side, the base is the lead here, and the collector is the lead here. These are all coming out of the bottom of this plastic package. This has a maximum power dissipation of about half a watt, and it has the maximum current, and this should be not in milliamps, but it's in amps, okay, about 0.8 of an amp, okay. So this is a fairly small transistor, which may or may not be useful for it will not be useful for a high current application. If we wanted to do another kind of transistor, a little bit more involved, is we can use a Darlington pair. And this is a tip 122 Darlington pair, and it looks something like this in this package, and it has a base, collector, emitter is indicated here. This is a little metal tab, and that metal tab is really good because you put a big bolt here, you bolt it down onto a heat sink, generally a big chunk of aluminum, and that will go through and pull a lot of heat off of this, which would allow you to actually put 60 amps through this transistor if you can keep it cool enough. Okay, the maximum current without a big heat sink is about 2 amps. The maximum power dissipation is about 2 watts. And the thing that's interesting, because it's a Darlington and we actually have 2 base to emitter drops now, okay, we have to multiply that by 2. And the base to emitter drop it gets up to about 1.5 volts. So these are the transistors you'll have, and the purpose of tomorrow's lab is to use these transistors to improve our power supply. That's the end of the video.